Chapter 4 Solar Radiation and Earth. Section 4.1 Nature of Radiation. All objects in our universe that have a temperature above absolute zero produce radiation. And this radiation is radiated from their surface to the surrounding environment. This energy irradiation is emitted as electromagnetic waves. So radiation has wave-like properties. And radiation also acts as a particle, and these particles are sometimes referred to as photons. Radiation moving away from an object travels at the speed of light. No faster, no slower. Many different types of radiation exist. We'll define 7 different types. And these types vary according to their wavelengths. Light is a form of electromagnetic radiation that we can visually perceive. Light has a wavelength of between 0.4 and 0.71 micrometers or microns. We get light from the sun. The sun's radiation is not all light, only a portion of it. Approximately 44% is in the wavelength band known as light. This graphic describes the wavelength concept. So what we're talking about when we talk about wavelengths is the distance from one crest to the next, as shown here. We have 3 different series of wavelengths, and the top one has the largest wavelength, the bottom has the shortest. So, as I said, there are 7 different types of radiation that I'm going to define. And the first one is gamma rays. So these are very, very short wavelengths. They're produced by extremely hot objects like neutron stars and pulsars and supernova. They also come from radioactive decay. So when an atomic mass decays, it releases gamma rays into the environment. X-rays are another form of radiation. Their wavelengths are a little bit larger. Ultraviolet is even larger yet. And ultraviolet is our wavelengths smaller than visible light, so they're next to visible light. Here we have visible light. So visible light, it has a wavelength band from 0.4 micrometers to 0.71. So in the rainbow below, we're getting into on the left side the ultraviolet, and on the right side the next wavelength band, which is called infrared. So infrared is a wavelength band that is larger than visible light. Larger yet are microwaves. And then in this diagram, the last radiation band that we want to define, type of radiation, are radio waves. So they have wavelengths that are anywhere from 1 meter to 100 meters from crest to crest. Visible light appears to us white in color, but it's actually composed of 6 different color bands: red, orange, yellow, green, blue, and violet. Of those bands, red has the longest wavelength, averaging 0.68 micrometers. Violet has the shortest wavelength at 0.41 micrometers. Now, only a portion of the radiation emitted by the sun is in the visible light band, 44%. The entire spectrum band for the sun ranges from approximately 0.1 to 4.0 micrometers. The band from 0.1 to 0.4 micrometers, or the edge of visible light, is called ultraviolet radiation. The sun's emission of ultraviolet radiation is approximately 7% of its total emission. 48% of the sun's radiation falls in the region between 0.71 to 4 micrometers. This band is infrared. Scientists further break down infrared into near infrared, which has a wavelength band from 0.71 to 1.5 micrometers, and the far infrared from 1.5 to 4 micrometers. Now let's look at the process of radiation emission from an object and how objects absorb radiation. Now, radiation is generated from an object by the conversion of other forms of energy. At the atomic level, this takes place when electrons are excited, and this causes the generation and release of photons. One way that we can do this is by heating up the atomic mass. The amount of electromagnetic radiation emitted by an object is directly related to its temperature. So the more heat that we add to this mass, the more electromagnetic radiation that is produced. So this diagram illustrates how photon emission works. So I said one way we can do this is by the addition of heat energy. So in A, we have this atomic mass, and in B, we add heat energy to the atomic mass. This causes the excitement of an electron. The electron jumps into a higher orbital shell, and then it releases a photon and returns back to its normal shell. The amount of radiation emitted by an atomic mass or by an object can be described mathematically. And this mathematical equation is called the Stefan-Boltzmann law. Now, the Stefan-Boltzmann law works best for a perfect emitter, sometimes called a black body. And the sort of verbal description of this law is the amount of radiation given off by an object is proportional to the fourth power of its temperature as measured in Kelvin units. And Kelvin, of course, is a way of measuring temperature, where absolute zero is equal to 0. The process of radiation emission causes a net loss of heat energy over time. So all objects are emitting radiation, and they will continue to emit radiation until they reach absolute zero, and then they stop emitting radiation in our universe. Now here is the Stefan-Boltzmann equation. And it looks scarier than it really is. The term E star represents the amount of emission, the amount of radiation being released by the object in watts per meter squared. It's equal to a constant, which is given below, called sigma. And that constant is constant. And you multiply that constant times the temperature of the object to the fourth power, and temperature needs to be measured in Kelvin. So the following table describes the relationship between temperature and emission. We're not using Kelvin, we're using Celsius. So the difference is just add 273. So the temperature of minus 100 degrees Celsius is equivalent to 173 degrees Kelvin. But anyways, let's focus on Celsius. So an object with a temperature of minus 100 will emit 51 units of radiation. If we increase the temperature by an interval of 100 to 0 degrees Celsius, the emission increases to 315 watts per meter squared. If we increase the temperature by another 100 degrees, the emission is 1,098. Now, notice the last column shows the difference from the previous value, and this value isn't staying the same. It's growing larger, and this is related to this fourth power law. So at the final temperature, 500 degrees Celsius, the emission is 20,244 watts per meter squared. Now, matter in the universe also has the ability to absorb radiation. And the process of absorption is pretty much the opposite of emission. The absorption of a photon by an atom creates heat energy. So you may have experienced this when you're out in the sun, that you can feel the surface of your skin heating up. You're absorbing photons that originated from the surface of the sun. So here we show the diagram. It's essentially reverse of emission. So a photon is absorbed by the atomic mass. It excites an electron, and that excitement leads to the addition of heat energy to the atom. Now, our atmosphere is interesting because it has the ability to filter out some of the radiation entering and leaving the Earth. The gray area there represents visible light, so we can see that for the visible spectrum, there isn't any absorption, selective absorption, or emission, pretty much, by the substances of water vapor, carbon dioxide, oxygen and ozone, methane, and nitrous oxide. But you can see in the long wave bands, carbon dioxide and water vapor play a very important role in having the ability to absorb these wavelengths, either coming from the Earth's surface or from the sun. This is important, as is carbon dioxide, methane, and nitrous oxide, because it creates the greenhouse effect. And without this greenhouse effect, the Earth would be much colder. Average temperature of the Earth's surface would be minus 18 degrees Celsius rather than plus 15. Wien's law is another law that we need to learn. It's important because this law, this mathematical law, describes the wavelength of maximum emission from an object or body. And it suggests that the wavelength of maximum emission of any body is inversely proportional to its absolute temperature. As a result of this law, the higher the temperature, the shorter the wavelength of maximum emission. So an object emits a spectrum, and the center of that spectrum represents this Wien's law. It is the wavelength of maximum emission. And I'll show you two spectrums in a minute. But here's Wien's law mathematically described. So lambda max is equal to a constant divided by a temperature, where lambda max is wavelength in meters or micrometers. C is equal to, or the constant is equal to 2,897, and T is the temperature in Kelvin. So let's look at the wavelength of maximum emission for objects of different temperatures. So if an object had a temperature of minus 100 or 173 Kelvin. Its wavelength that emits the most radiation is 17 micrometers. If you increase the temperature to 0 degrees, 100 degrees warmer, the wavelength of maximum emission gets shorter. So now it's 10.6. And it continues to get shorter until we reach 500 degrees. It's now 3.7 micrometers. 15 degrees Celsius represents the average temperature of the Earth, or 288 Kelvin, and the wavelength of maximum emission from the Earth's surface and atmosphere is approximately 10.1 micrometers in the wavelength in the long wavelength band. 5,527 Celsius or 5,800 Kelvin is the temperature of the sun. Its wavelength of maximum emission is 0.5 micrometers, which is in the visible band near the color purple-blue. So let's look at two spectrum graphs, one for the Earth, one for the sun. So these graphs illustrate the relationship between the temperature of the body and its emissions of electromagnetic radiation. Note the following two things. The amount of radiation emitted from a body increases exponentially with a linear rise in temperature, and two, the average wavelength of emission becomes shorter with increasing temperature. So the average temperature of the Earth is 15 degrees Celsius. As I said, its wavelength wavelength of maximum emission is about 10 micrometers. On the y-axis, we can see the intensity of the radiation being emitted. So at 10 micrometers, it's about just over 25 watts per meter squared. The graph below shows the spectrum for the sun. Notice how it's shifted to the left. And this is because the sun has a much higher temperature. It's not 15 degrees Celsius, but 5,527 degrees Celsius, or 5,800 degrees Kelvin. Now, the wavelength of maximum emission is 0.5 micrometers, and the intensity of that radiation is about 90 watts per meter squared, so much higher than the Earth. The total amount of emission, if we measured everything under the curve for the sun, would be approximately 64 million watts of radiation being emitted from the surface of the sun. Now the sun is amazingly bright. Its surface represents a light bulb that is putting out 64 million watts per meter squared. Well, obviously that's not what we're receiving at the Earth's surface. It somehow has become diffused or less intense. And this law, the inverse square law, describes how solar radiation traveling through space from the sun's surface to the Earth becomes less intense. And as radiation travels away from a body, its intensity decreases exponentially. And the inverse square law suggests that the amount of radiation passing through a specific area is inversely proportional to the square of the distance of that area from the energy source. Well, that's a mouthful. What does it mean, though? And we can describe this quite simply with a graphic. So here we have a beam of light beginning at the top left-hand corner, and it travels three distances, and you don't have to worry about what that distance is, but they're equal. There's distance 1. It travels from the original source to distance 1, to distance 2, to distance 3. And the only thing you have to keep in mind is that these distances are the same. So we can model that at distance 1, that radiation is covering that 1 square. If it moves to distance 2, it's now spread over a much larger area, 4 squares. So intensity equals the intensity of the radiation divided by distance squared. So the distance now is 2. 2 squared is 4. If it travels further out into space to distance 3, 3 squared is 9. So it's now spread over an area of 9 squares. And of course, less intense. So the intensity of the radiation at distance 1 would be 1. The intensity of the radiation at distance 2 would be 1/4. The intensity of the distance of the radiation at distance 3 would be 1/9. Now, if we went to distance 4, 4 squared is 16. The intensity of the radiation there would be 1/16 of what it was at distance 1, and it would be covering 16 squares. If we went to distance 5, 5 squared is 25, so now it's spread over 25 squares, 5 by 5, and the intensity of the radiation is now 1/25. So from the sun's surface, the intensity of the radiation is 64 million watts. By the time it gets to the edge of the Earth's atmosphere, it's been diffused to only approximately 1,370 watts.